Hi there. We're getting ready to start a new unit called Aqueous Solutions. You may remember from earlier units that aqueous means it's a solution in water. So before we get into solutions, we need to go back and review water. The first thing we need to look at for the water molecule is the shape. The water molecule has 3 atoms, 2 hydrogens and 1 oxygen. And when you do the Lewis structure, there are 2 bonds and there are 2 lone pairs around the oxygen. So when you have 2 bonds on a molecule and then 2 lone pairs, that's going to make a bent or V-shaped molecule. And our bond angle here is 104 degrees. Oxygen has a higher electronegativity than hydrogen, so it's pulling all those electrons up towards it. And when you blend this with the bent shape, you have a very polar molecule. Here's another look at the polar molecule of water. You can see how the electrons are pulled up here to the top around the oxygen, making it slightly negative. And then down here where the hydrogens are, it's slightly positive. And so we have a dipole of charge, like a little mini magnet. Now that we've looked at how the hydrogens and oxygens are held together within the molecule, let's talk about how an individual water molecule is held close to another water molecule. Those are called intermolecular forces between the molecules. And the strongest one that occurs with water is called hydrogen bonding. A little bit of a review. Hydrogen bonding occurs when you have molecules that have a hydrogen bonded in the molecule to a fluorine, oxygen, or nitrogen. That causes the hydrogen to be extremely positive, and the fluorine, oxygen, or nitrogen, oxygen here, are extremely negative. And so they stick together like little mini magnets. But these are not full bonds. These are just handshakes between. However, hydrogen bonding is very strong, so water molecules make very strong handshakes with each other. This hydrogen bonding is going to account for most of water's special properties, such as high surface tension, capillary action, adhesion and cohesion, low vapor pressure, the density of ice, high specific heats and heats of fusion and vaporization, high melting and boiling points, and water is known as the universal solvent. Many of these properties we've already talked about in earlier units, but there are a few that we have not talked about yet. And of course, we're moving into the aqueous solutions unit, and that's where we'll be dealing with water as a universal solvent. Here's one of the new properties. This one is surface tension, and here's your definition. It's the inward force or pull that tends to minimize the surface area of a liquid. In other words, it's what holds the liquid surface together. For example, when you have drops of water, because it has high surface tension, they tend to make a spherical shape as the surface tries to completely pull inward. Paperclip. If you're careful, you can make a paperclip float on top of the water if you don't break that surface tension. There are bugs and lizards that can actually walk on the water because they're able to spread their force out so much on their legs that they don't push through or break the surface tension. Here's another definition. A surfactant is any substance that interferes with that hydrogen bonding and reduces the surface tension. It's sometimes called a wetting agent. One example of a surfactant is soap or detergent. So how does that work? Soap is this very long molecule, and it's got a very long non-polar tail, we'll call it. Well, that non-polar tail is attracted and makes handshakes, intermolecular forces, with the non-polar oily dirt. The top part of a soap or detergent molecule has a polar area. So it's attracted with water by hydrogen bonding or dipole forces. And so if you get enough of these little soap molecules, they kind of stick their tails down in the oil, and then their polar heads help pull it off into the water, and you break up the oil. It also will have the effect of breaking up the water itself with these little bitty oil particles, and so it interferes and reduces surface tension. Another example of where this was used is they used the dispersant on the Gulf oil spill in order to make that oil dissolve in the ocean. Here's another surface property, another definition. Capillary action is the ability of a narrow tube to draw a liquid upwards against the force of gravity. This occurs when the adhesive intermolecular forces between the liquid and the solid of the tube are stronger than the cohesive intermolecular forces within the liquid. Okay, let's break this down. What does adhesive mean? Think adhesive tape. It's where the water sticks to something else. In this case, the solid part of the tube. Now, cohesive means that water sticks to itself. So we're saying that it's easier for water to stick to the tube than for water to stick to itself. So how does that actually work? Look at these different pictures. This is water with green food coloring in it, and we have different size tubes. The smaller the tube diameter, the higher the water has been able to pull itself up. So it's sticking to the walls of the tube, and then the cohesive hydrogen bonding has the water pull itself up. How about an example from bio? Let's talk about trees. I have 75-foot pine trees in the front of my house. When it's hot summertime, I don't stand there and shoot the water up to the top of the trees to get all the pine needles to make them green. That would be silly. Of course not. No, I water the ground, and then the tiny little capillaries in the tree trunk pull the water up to the top of the tree. Same thing happens in your body. Our heart can't pump hard enough to push all of the blood and fluids all the way to our fingers and our toes. So we have tiny little capillary veins that help pull the blood through our body by capillary action. Another example of capillary action is something we see in the lab. Every time we work with water or water solutions, we get a meniscus. So how does this form? The water molecules have adhesive forces, which causes water to stick to the glass. It also has cohesive forces where the water sticks to itself, so it stays down in the bottom. So we end up with this curve as the side water molecules try to walk up the glass. That's why there is a meniscus when we are reading water in a graduated cylinder. Now, mercury has very weak adhesive forces. It doesn't stick to the glass well, but really strong cohesive forces because it's a metal and metallic bonding is very strong. So it actually forms a dome and does not form a meniscus in a piece of glass. Another special property of water caused by hydrogen bonding is water has a low vapor pressure compared to other liquids. Vapor pressure is caused by the tendency of molecules to escape the surface of a liquid and enter the gaseous phase. And so it's the pressure of all those particles that have escaped from the liquid. Now, the low vapor pressure of water is due to hydrogen bonding holding those molecules in the liquid phase. Or in other words, because hydrogen bonding is such a strong intermolecular force, it's hard for those water molecules to escape and become a gas. Another important property of water is that the liquid water expands when it freezes because the hydrogen bonding causes it to make these big open hexagonal crystal structures. And so the density of ice is less than the density of liquid water, so ice floats. We talked about this way back in the beginning of the year in the matter unit. That's why every snowflake has 6 sides, because every snowflake has a hexagon at its heart. Chemistry cat time. Ho, ho, ho. Water joke. Get it? HOH, H2O, it's water. In earlier units, specifically thermo, we talked about how water and that strong hydrogen bonding causes it to have high melting and boiling points and high specific heat and heats of fusion and vaporization. So what's left about water? Discussing it as the universal solvent in our unit on aqueous solutions. So stay tuned.